Go hands-on with the new Micro Modular Controllers that we introduced last week. Um, the presentation's about 25 minutes long, but as usual, if you have any questions, feel free to pop them in and we'll get to them at the end.
Hello and welcome to today's webinar. Today we will look at hands-on with the new Micro Modular Controllers. Let's take a look at our agenda for today. We are going to start with a quick introduction to these new CPUs. We are going to give you a hardware tour. We will talk about comms and connectivity. We are going to talk about I/O expansion and show you how to do physical assembly, and then we are going to demonstrate how to connect with Cscape, and we are going to exercise the I/O on the bench, and we will finish with a Q&A session. These are the new Micro Modular Controllers, the CPU200 and the CPU250. These are the two newest members of the Horner Micro series. These are not all-in-one controllers, but they share a lot of commonality with the Micro series and can be used in a lot of the same applications. They both have enough memory and built-in I/O to cover most simple applications, and they include a modular I/O expansion and a CPU logic capacity that allows it to swing above its weight or to handle even larger applications. And generally, these particular CPUs are going to be used in applications that do not need a screen. We are going to do a tour of the hardware next. We are going to show these slides just briefly on the screen. Most of our work is going to be done just showing you these on the bench during our demonstration. So here's what the CPU250 looks like with a couple of OCS I/O modules plugged into it. And here is what the CPU200 looks like, also with a couple of OCS I/O modules plugged in. When you purchase these products, there is no OCS I/O included. Let's take a physical look at our CPUs. Here is the package. You can see size-wise it fits into our palm of our hands. As we take a look at the hardware, we can see that it is DIN rail mounted, also comes with a black plane, also comes with a back plane connector installed, which can come out. Do not worry, you cannot install it backwards or upside down. It can only go in one way. That is for adding OCS I/O off to the side if you want to do that. Also, let's take a look at what else we have here. We have a standard OCS power plug, 3 pins, and this will take up to 12 gauge wire. Now, we do not see any reason to use a wire that large, but it is available if you need it. We would recommend 16, 18 or 14. Any of those would be much easier to work with than 12. We tend to lean towards 16 and 18 based on current capacity and everything else. Also, we have got a micro SD slot up here. As you can see, we have got one connected there. The front of the micro SD slot is on the left and the contacts are on the right, so if you just slide it in, push it down, and you are good to go. Also, we have got a stop load switch. It has got 3 positions. In the upper position or the run position, you can see that also maintained. We can move it to the stop position, which is also maintained. And if we want to load a program, this is a return to center or momentary type action on the load button, so that is available here. And then we have plenty of status LEDs over here for power run, module status, network status, the same type of LEDs you find on the Horner products all the time. Also have an LED indication on the LAN port and LED indication which you cannot see. You will see later on the bench when we power it up that you can actually see the LED indication on each of the I/O connections as well. So that is the physical look at the CPU250. And then we also got the CPU200 here, which is identical every way except it does not have built-in I/O. It depends strictly on additional I/O through OCS I/O, which you can add to CPU250 if you need more than what is built in. One other little difference we will show you here on these two units we have here. The unit on the right, CPU200, is a pre-production unit. You can see the switch is a little longer than the switch on the CPU200 on the left. What you receive with your production unit should be a shorter switch. So this is the look at our two CPUs. As we continue to explore the hardware of these two new products, let's talk about CPU memory, because this is an area in which these products exceed what is normally available in the rest of the Micro series. That is what allows them to handle larger programs. They can handle larger programs from logic memory standpoint with 2 megabytes of capacity, and they can also handle more variables with 50,000 words and 16,000 plus Boolean variables, and they have plenty of floating points support and PID loop support, just like the rest of the Micro series. When it comes to connectivity, they are loaded and we are going to go through these primarily on the bench. We are leaving this up here just briefly so you can do a freeze frame if you want a summary. Let's take a look at connectivity. Let's start with USB-C. It is strictly for programming, but it offers best performance for a download standpoint. From a data watch standpoint, you can also perform firmware updates through USB-C. So USB-C is the only way to go for programming. Although Ethernet works fine, it does not have the same performance as USB-C. Let's talk about Ethernet. What can we do with Ethernet? Well, if you need to connect to some sort of SCADA system or control room over Modbus TCP, this here can be a Modbus TCP server, but can also be a client. So if you need to connect to a variable frequency drive or server drives or other devices, Modbus TCP client is one avenue to take. Again, with Modbus TCP, you can connect with anything. Now for those of you who are looking for connectivity in Rockwell environment that supports Ethernet IP as a server, which means it cannot be a scanner, but it can sit on Ethernet IP network and be pulled or connected to a Rockwell device, where the Rockwell device maybe is controlling a machine, and this is controlling a prohibitable on the machine. So it has a good Rockwell connectivity through Ethernet IP server. From a serial port standpoint, what if you want to interface to a low cost variable frequency drive, for instance? Well, Modbus RTU is built in there, and just about every drive features Modbus RTU built in for free, even low cost drive. So this is a good option here. Barcode readers, serial printers can also be connected through serial port. CAN can be used for a variety of things, including adding I/O expansion beyond locally. So local I/O expansion is done over here, over OCS I/O. You can connect remote OCS I/O based up to 16 of them through this CAN port here. And we also support J1939 as well as CAN Open. CAN Open, more for real bus, support J1939 for those mobile applications. Now let's talk about I/O, and the CPU250 has an array of I/O built into it, 34 built-in I/O points in total. We're going to go through all the details on this during our Cscape connectivity and configuration portion of the demonstration today. But again, we will leave this up here as a summary for all of the I/O capability that is built into the CPU250. And a reminder, the CPU200 does not have built-in I/O. It depends on expansion I/O, but both of CPU200 and the CPU250 can be expanded with up to 7 standard OCS I/O modules plugged straight into the side of the normal OCS I/O backplane. So local I/O here is available as an expansion with OCS I/O. And what OCS I/O modules are available? Well, this is a product line, more being added all the time, but these are the modules that are currently available, and we have several more we will be launching later on, so lots of choices. If you need to add relay, add relays. If you need to add more analog, add more analog. Whatever the case may be, you have got the option with OCS I/O. So let's show you how to go ahead and add additional I/O to CPUs through a demonstration. So what we are going to do is we are going to put our CPU on the DIN rail, and we are going to add 3 OCS I/O expansion modules. Let's start with the CPU. You can see we have got our backplane connector pre-installed. That is how it comes from the factory, but if it is loose, you can just plug it right back in. It only goes in one way. Let's start by putting it on the rail. Make sure the top is pushed in, and now it is on the rail. So we have got our 3 OCS I/O modules we are going to add. They each came with their own backplane connector, and we are going to assemble those now. And then we are going to push them up tight against the CPU. And then we are going to assemble our OCS I/O modules, and we can use the DIN rail as a fulcrum, the top rail of the DIN rail, and just plug them in that way. So that is the assembly on the rail. Next, let's make sure that we have these secure. So what we are going to do is we are going to add these clamps to the DIN rail. We are going to back that off a little bit so that this piece of metal here is close to the edge, and then we are going to assemble it on each side because we want to make sure that we have it secure on the I/O and the CPU. We are going to start with installing these clamps here again. Make sure this is backed off so we can get it easily on the rail. Get our screwdriver in there, and we have got a stack of 3, but we can also have as many as 7 OCS I/O modules with our CPU and our end clamps. And if this was a CPU200, the process would be identical. Here we are in Cscape 10.1 Service Pack 1, and now let's try and establish a connection with our CPU. We are going to be connecting to the CPU250, so let's go to the connection wizard first. And we would like to talk to the CPUs over USB. It gives us best performance both for downloads as well as updates with data watch. Selected USB. It came up as COM3 on our computer. We are connected. The CPU is in stop or IDL mode here, as you can see. Now let's go to the hardware config because UCP was not connected when we fired up Cscape. We are still showing the default controller here for the connection. So let's select from the OCS I/O CPU series here the CPU250, which matches what we have. Now let's go ahead and finish the configuration process. So we will go back into the hardware configuration and let's take a look at local I/O. Everything else in terms of LAN configuration is standard. That is the normal default LAN configuration here. Cscan is selected by default. Let's look at the local I/O configuration, which is going to be different and new. So we have got over 4 different areas of configuration with built-in I/O, just like we have these same 4 different buttons for built-in I/O for an OCS all-in-one controller. So we will go through that and take a look at the details here, but we also have the ability to add OCS I/O modules to the side. So let's go ahead and do an auto-populate I/O, because in our case we do have some I/O connected here. So let's hit auto populate, then asks us are we sure we want to do that, because it will bring everything back to default from a configuration standpoint. So we are going to say yes, and there we go. We have got our 3 I/O modules that auto populated. Let's go ahead and configure this I/O, starting with digital inputs. We can select between positive or negative logic on the digital inputs. We can also select whether we want to use high-speed counting on the first 4 inputs. So we have our standard high-speed counting options that we will find elsewhere in the Micro series. That is the options we have under digital inputs. On the digital outputs, that should look familiar. As well with the one addition, we can have normal Q1 and Q2, which are 2 high-speed capable outputs, can be selected for normal operation, PWM operation, or frequency. You can use the outputs to fire based on encoder position. For instance, everything else is similar for the digital output. Now let's take a look at these flexible inputs. So we have 8 standard digital inputs that we have already talked about. Now we have 8 flexible inputs. They can either be digital or analog. When you use them as digital, you can select the range as either 24 volts, 12 volts, or even 5 volts. Or you can set a custom on and off threshold. We are going to leave these at 24 volts, but you can also select analog for each point. And again, this is configurable on a per point basis, and the analog can either be 0 to 10 volts, 0 to 20 milliamps, or 4 to 20 milliamps. And you can configure the scaling so full 0 to 32,000 if you choose, or you can knock it down to 0 to 4,000 plus or minus 2 or 0 to 1,000. So lots of options here on the scaling. Even again, these are all settable channel by channel. You also have filtering, so if you set your channels for analog, you're going to want to filter the values so you have a good mix between stability and responsiveness. And 0 is no filtering, 7 is max. Digital channels that you select, you can select between positive and negative logic. Now, what are all these config registers, config blocks? What are these? Well, this is an advanced feature where you can assign variables to these if you choose and configure the flexible I/O on the fly. So as an OEM, if you want to be able to have different options for your customers that run the same Cscape program, you could change your I/O configuration on the fly. There we go. On the flexible input side of things, on the analog output side of things, we have got 4 milliamp based analog outputs, we have got 0 to 10 volts based outputs on the milliamp side. You can disable each individual output if you choose. If you choose, select between 0 to 20 or 4 to 20. Also select the scaling on the output side of things. Then on the voltage side of things, you can either disable them or leave them at 0, 10 volts. All these can be set on a channel by channel basis, and in terms of holding last state, if the controller goes into stop mode, this is where you can decide, do you want to have it freeze as its current value, or go into minimum value, or go to the maximum value, or go to the median or middle value. In the case of 0 to 20 milliamps, that would be 10 milliamps, but generally we select minimum 4 to 20 for our input ranges and 0 to 32,000 for our data ranges. For voltage, we do the same thing, 0 to 32,000, 0 to 10 volts, and minimum. But again, these are all set double channel by channel, and once again, you can set them on the fly if you prefer. We have not finished yet. Let's go back into the edit IO here, and since we have IO added, we want to add a status block. What is a status block? Well, this is a 10 consecutive integer. It is a variable we are going to assign here 10 consecutive integers, which is going to allow us to see the status of the IO. So in this case, we could do something like OCS IO status, and we can hit the config button here and set that for a dimension of 10. That is how many words we have here, and we have got that configured. And then the default for where your OCS IO expansion starts in terms of addresses, leave it at the default. You can change that if you want, but there is no reason to do so. We have added our status register. Now let's go in and take a look at how to configure the OCS IO modules. Now this is a standard configuration you would do on any OCS IO module. Again, this is the ADU module we have here, which is a universal analog input, 16-bit. And we can set things like filtering, we can set the range, which you can see this is a flexible module, and we can set the scaling if we choose, and you can change the configuration on the fly. And then you can also change how often this is scanned, how often we are going to take an update from this. So that is the ADU. We have also got DAC here and a relay module as well. Now if we want to see specifically where the IO addresses start for each of these three modules, we can go into more info tab here, and it will show us where our AI, AQ, and Q variables start for each of these three modules. Now remember, these are zero-based terms shown in this dialog. So the way this is written here is zero-based. So if you're going to use addresses, it is %AI 17 through 20%, AQ 25 through 28%, and AQ 32 through 48. So that is the hardware configuration for the CPUs. Before we do our bench demo, let's go through with you another useful piece of information when you are starting with a new controller from Horner, and that is what is the IO map that is used with that particular controller. We are going to have these up on the screen here for you. All this information is available in our users manuals for new CPUs. The IO that is built in all starts with I1, Q1, AI1 and AQ1. This table shows you how it is allocated, and then when you start adding expansion IO, there are the starting IO registers for expansion IO. They are at the bottom of the screen. When you are using the high-speed counter that is built into the CPUs, here is the IO map for that functionality. You can see there is different IO map whether you are using totalization, frequency, or pulse versus quadrature. Now if you are using high-speed outputs, there are a couple different ways you can use them. One is as a PWM. We have got the memory map shown here on the right for that, and then on the left there is a stepper functionality. Now when you add OCS IO, you have to add that status register so you can get the status details, and here is the details on what the status information gives you. Let's take a look at how we are exercising our CPU 250 today. We are going to use our IO stimulator. We have got loads of ways of stimulating IO, from digital inputs to digital outputs to encoder signals. We can stimulate analog input signals. We can stimulate RTD signals. There are a million ways to connect this. First of all, the first four inputs, as we have mentioned before, are capable of high-speed signals. So what we have done is we have connected the encoder to inputs 1 and 2 here. So inputs 1 or 2 are configured for high speed. And this is a quadrature based encoder. And then we have got 8 physical input switches, which we have wired to inputs 3 through 10. Those are set for just physical inputs. Now starting at input number 9, we have 8 consecutive flexible inputs. We have configured the first 2 flexible inputs just as standard DC inputs. To connect here is our digital input signal. These last 2 digital input signals, which are these light switches here, and then the next 2 of the 8, inputs 3 and 4 of the 8 flexible inputs, we have set for 4 to 20 milliamp input. So those are inputs 11 and 12, and they are flexible, so they are configured for 4 to 20 milliamps. Now let's go to the output side. Now our first 2 digital outputs can be usable for high speed. We have configured them for high speed, and we can see the status for those high speed signals here, which are currently off. Now the next 6 digital outputs are those outputs 3 through 8. Those are configured as standard DC outputs. Now we do have the ability here to add a couple of these test leads from our multimeter for testing milliamp outputs. If we had wanted to connect up maybe the milliamp 1 output here, we could have done that. We do not have any analog output testing happening here. And then the signals for the RTD pot, those are connected here to our first expansion module, which is our 4-channel ADU100, which is a universal 16-bit analog, in which can support RTDs and thermocouples, in addition to standard 4 to 20 milliamps, 0 to 10 volts. So we have got channel 1 here of our RTD pot set for RTD signals here on the ADU100. And we have got a racing pattern of LEDs 3 through 8, which you can see here, that is in our program. You can also see that we do have LED indications on the terminal strip, so you can see that working. Now on our high speed outputs, what we have got that configured for is if we flip switch number 1, then our high speed outputs turns on, and we have got that set for a frequency of 5 Hz, just something that we can easily see on the bench. And we have done the same thing on switch number 2. So if we flip the switch number 2 up, we have got our logic program to turn on a PWM signal at 5 Hz on the second high speed output. So to exercise the encoder and the analog inputs along with the RTD, we turn to the data watch. We have got variables that are tied to all those inputs here on the screen. Let's start with the encoder position. So that has a value of 0. If we turn the encoder wheel on, the stimulator, you can see that counting up. On the first of the 2 milliamp pots, we will go ahead and increase the signal here. We have got that configured from 0 to 1000, scaling approximately. And then on the third one, we will go ahead and start moving that down on the milliamp input. And then on the RTD, we are going to go ahead and slightly turn that pot here on the downside, will cause our temperature to go up here. And in reverse, if we move the pot in clockwise direction, you can see our temperature going down. So on the I/O stimulator, the potentiometer has an inverse relationship with the temperature value here. That is exercising the I/O that we have on our bench. Let's go ahead and take a look at how we configured the I/O. Now that we have exercised it, we are going to go to the hardware config and go to the local I/O tab, and then here are our 4 normal I/O configuration buttons for the built-in I/O. Let's take a look at how we have got the inputs configured. Positive logic for everything. Quadrature on the first 2 inputs. 1 leads to the count up is what we have configured that for. That is the digital input. On the output side, we do have the first 2 outputs. Here is where we have configured those for high speed. On the flexible inputs, the first 2 inputs are set for digital 24 volt range, and the next 2 were set for analog. So these are the 2 connected to the last 2 switches, which is 7 and 8. These are the 2 selected to the 2 milliamp pots on our I/O stimulator. We did the scale from 0 to 1000 on the analog input side. We did not do anything on the analog output side. Now let's go take a look at how we have configured this ADU100 and the other modules. So we will double click here, and you can see here that we have disabled all the channels except for the first one, which we have set for RTD PT 100 degrees C temperature range Our data is now coming back in 10th degrees Celsius increments, and we have configured that at the default of updating readings every 100 milliseconds, and then everything else is default. We did not do anything with the analog output configuration or the relay configuration, so that is the I/O configuration that we have here on our demo. Just to run you through the logic real quick, just to show you what is happening here. This is some logic for creating recent LEDs. This is the logic that turns on and off our 5 Hz output. We have a variable for duty cycle and another one for frequency. Duty cycle is scaled for 32,000, so for both of the two PWM, we have it set for 50%. So 16,000 of the 32,000, which is the scale, means a 50% duty cycle. And then the frequency variable is where we set our frequency. We vary between 0 or 5 Hz depending on the position of the switch, and we have the appropriate analog output registers tied to these particular variables. Let's take a quick look at those now. Let's go to the program variable here. Here is our program variables. And if we go to our global variables and we go down and take a look at our duty cycle and frequency for our two PWM, you can see those are tied to AQ 13, 15, 17 and 19 as double integers, because those are the control registers for PWM. On the RTD input side, we are just reading in the value from the ADU 100, that first channel there, as a raw input, and doing some scaling on it. We have an additional relay exercising that we are using for our relay outputs that are tied to the relay module that is connected there on the bench. Now let's take a look at the high-speed counter variables, because when we go to the data watch, we had an encoder position variable. Let's take a look at that. So we will go back to the program variable window and we will find the encoder position variable, which we have found here. And that one is tied to the accumulator of high speed counter number 1, which is AI9, is the analog input register here. So we have tied that to a double integer value over to the encoder position variable. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so we're going to continue on with the Micro Modular Controller next week, where we use the CPU250 with stepper motors. So that registration link is up if you would like to partake in that. But if you would like to go back and rewatch this video, we will have it uploaded to the website as usual. I don't see any questions on this, so I think we can leave it there for today. Thank you all for joining us, and I will see you next time.